going to move away from alternating series and look at some other types of series. Remember, in this section here, we started to develop the concept of how we handle whether a series converges or not when all the terms are not positive. So in previous work, when we were using our basic comparison test, limit comparison test, integral test, the series had terms who were always positive. And we're moving away from that now. And so let's take a look at this series here. So consider the series, the sum from n equals 1 to infinity, sine of n over n squared. And if we were to expand this a little bit, we'd get the sine of 1 over 1 plus the sine of 2 over 4 plus the sine of 3 over 9. I'll put one more plus the sine of 4 over 16. And then, of course, it's going to continue like that indefinitely. Now, you may not see any negatives here. That doesn't mean they're not there, okay? So sine of 1. What is the sine of 1? Well, just pausing so you can think about that for a moment. You may remember approximately what 1 radian is as a measurement, but if not, we're going to talk about it. But it'd be worth thinking about for yourself if you want to pause it a little bit. It'd be worth actually thinking about all of these terms here and seeing if they're positive or negative and how the pattern is determined. Anyways, sine of 1 is about 57 degrees, so it's going to be somewhere over here. And remember, sine in the first quadrant is positive, and so this first term is positive. Sine of 2, well, you just got to double that, and so it's going to be somewhere over here like this. It's still positive. Sine of 3 radians is almost pi radians. Of course, pi radians is 3.14159 and so forth. And so 3 radians is over here somewhere. I might be a little too close to the horizontal axis, but I'm not measuring, and I'm just trying to give you the sense. So that's still positive. 4 radians is down over here somewhere, and now we have a negative. And then sine of 5, the next one, is going to be over in the fourth quadrant. Sine of 6 is also in the fourth quadrant. So we're going to have some positives, we have some negatives. They're not alternating in the sense that every other term is positive and every other term is negative. So how are we going to handle this type of series? All right, sorry about the dog interruption. I'm not quite sure the last thing I said, but nonetheless, this series does not follow an alternating series pattern. The terms are not all positive, so we can't use the basic comparison test or the limit comparison test. The nth term is going to 0, which tells us nothing. And so we're sort of stuck right now. Like, what do we do to determine what's happening here? Well, what mathematicians in this case too is they say, let's do something related to it. We can't solve this one at the moment, so let's look at something else. And then hopefully looking at this other thing might give us some information about what's going on here. If you can't solve the problem you need to solve a related problem, and then maybe that'll give you some insight. Now let's take a look at this series. If I look at this series here, now all the terms are positive because I just took the absolute value of each term. And so I can now use the earlier test that we developed. I can use either the integral test or the basic comparison test or the limit comparison test. I'm not going to use the integral test, but I can use one of those other tests that I mentioned and come up with a conclusion here. So let's see what I can do. Now, we know algebraically that sine of n is bounded between -1 and 1. So if I take a look at the absolute value of the sine of n, that's going to be bounded between 0 and 1. All right. So we get that. Now I can divide through by n squared. I still end up with 0 on this end over here. I get the absolute value of sine of n over n squared, and then less than or equal to 1 over n squared. Now, just a slight little bit of algebra here. N squared is always non-negative to begin with, so this is going to be exactly the same thing as if I take sine of n divided by n squared and then take the magnitude after the fact. And that's still going to be bounded by 1 over n squared. So the terms of my series up here are all bounded by the terms of the series 1 over n squared, and this is from n equals 1 to infinity. Excuse me there. And so we know this is a convergent p-series with p equal to 2, which is bigger than 1. And so by the basic comparison test, some other books use a different name for the basic comparison test, but that's what our book uses, so that's what I'm using. Then the series is also going to converge. The series of sum from n equals 1 to infinity, absolute value of sine of n over n squared is going to converge. Now, so what? That wasn't what we were trying to solve. I mean, we were trying to solve way back up here whether this series converged. And all we know is now it's series formed by its magnitude does. You might be saying, so what? Well, again, hopefully this will tell us something. Let me give you a definition first, and hopefully there'll be a connection between these two series. Knowing that this series converged will tell us that the original series that we were considering converges also. So here's the definition. There's two parts to it. The series A sub n is absolutely convergent if the series formed by the magnitude of the terms converges. So in other words, if you take the absolute value of the terms and look at the sum, that sum there, then we call the original series absolutely convergent. So the series that we were considering before is absolutely convergent because, as we showed up here, the series formed by its absolute value, terms, the absolute value of the terms is convergent. So that original series is absolutely convergent. Second part of the definition, the series A sub n is conditionally convergent. And this is, okay, so absolutely convergent was what we're defining here. Conditionally convergent is what we're defining here. If the series, I'll move this down here. If the series A sub n converges, but the series formed by the absolute value of its terms diverges. So there are two different types of convergence here. Absolute convergence and conditional convergence, or something being absolutely convergent or conditionally convergent. All right, so let's talk about some of these for a moment. Let's first say you know a lot of absolutely convergent series because any series that was positive termed and convergent, well, automatically it's going to be absolutely convergent. Because if I take the magnitudes of the terms, then it's just going to be the same series anyways. So again, if we have a positive term series and we know it converges, it's automatically absolutely convergent because if I take the absolute value of the terms, I get the same series. Now, do we know any conditionally convergent series? We actually do. Let's think for a moment here. We've shown and talked about the alternating harmonic series already, and we know that this converges. It doesn't matter where you start it. You started with a positive, you started with a negative, it's still going to converge. But we know the harmonic series itself diverges, which is the absolute value of the terms in the alternating harmonic series. And so the alternating harmonic series is a conditionally convergent series because it converges, but the series formed by its absolute value diverges. Okay, so you already have some familiarity with some series with these properties. We just didn't call them those things, and now you're aware that that exists. Now, wouldn't it be nice if one of these things told us about the original series, specifically if number one told us about the original series, and it does. We have a theorem that connects these things back together. So the theorem is this: if the series A sub n is absolutely convergent, then it is convergent. All right, short and sweet here, but this is great. What this tells us is that now I can take a series whose terms are not all positive and form a series of by the magnitudes of the terms, make them all positive, and then I can start using my other tests. If the integral test is applicable, I can try the integral test, or I can try the basic comparison test, or the limit comparison test. And if I can show the series formed by the magnitudes that converges, then I know the original series converges. So now I've just opened up my arsenal a little bit, and I can use more tools to try to prove a series is convergent, even though the terms might not all be positive. Okay, so I can look to see if it's absolutely convergent. Now, although in class I would usually prove this theorem, I'm going to forego the proof right now just for the sake of the length of the video. At some point, when we come back together, we could go over the proof together. So here's example number 4. Determine whether or not the following series is convergent or divergent. If it is convergent, classify it as absolutely or conditionally convergent. All right, so I would really want you to pause the video and to go give these a try, or at least try the first one, and then you can come back on and see how it's going, and then subsequently pause and work on the rest. The point is that you got to get somewhere along your skills have to get strong enough so you can handle these without my help. Now, I know some of this is still very new and we might be struggling with it a little bit, but if you just watch me do it without even trying it a little bit on your own, you're not going to be as good at this eventually as you will be. Every little bit contributes. It's, it all benefits you if you do a little bit more on your own than with a little bit from me. Anyways, let's go ahead and take a look and see what we're going to do here. Okay. Well, this first one here has this sort of odd exponent. And I don't mean odd as always odd. It actually doesn't work like that. It's peculiar. N times n plus 1 over 2. So if you start looking at the terms of this one a little bit, if I plug in 1, we get 3 in the denominator. But what's the numerator? It's going to be 1 times 2 over 2, which is 2 over 2, which is 1. And negative 1 to the 1 is going to be negative 1. If I plug in 2, I'm going to get 2 times 3 over 2. And the 2's are going to cancel and be left with a 3. And negative 1 to the third power is still negative. So this is going to be minus 1/9. If I plug in a 3, then I'm going to get a 3 here and a 4 here. Now that's 4 divided by 2 is 2. 2 times 3 is 6. Now negative 1 to the 6 is positive. This is going to be plus 1 over 27. So negative, positive. If I plug in 4, I get 4 times 5 over 2, 20 over 2, or 10, which is going to be another positive, so 1 over 81. If I plug in a 6, then I'm going to get 6 times 7, which is going to be 42, divided by 2 is 21, so that's going to be minus 1 over 243. And then it's going to be minus again, and this can be plus a couple times, and it's going to keep going back and forth, and negative, positive, and so forth on down the line. So it's not an alternating series in the same way that we're used to alternating series. And so we got to use, terms are all positive, so I can't do something else. So let's see if it's absolutely convergent. So if I look at the series formed by the absolute value of the terms n times n plus 1 over 2, 3 to the n, then I'm just looking at 1 over 3 to the n. This is from n equals 1 to infinity in both cases. Oh, what's that? Hopefully you recognize this as geometric, okay? So this is a convergent geometric series with, and how do we know that? I don't need to, why is my computer slowing down? With the magnitude of r equal to 1/3, which is less than 1. All right, so this is going to converge. Therefore, the original series will be convergent, or is absolutely convergent, and therefore convergent. And so this, actually, I should be a little more complete for you here. From 1 to infinity, -1 to the n times n plus 1 over 2. If you can't read that, that's okay. Is absolutely convergent, and therefore convergent. So please go pause the video and go try part B on your own and see what you can come up with. Part B is the sum from n equals, I'm not sure if let me check here, from 1 to infinity. And we got -1 to the n over the natural log of n plus 1. This one is just a normal alternating series, so I can just see if it converges using the alternating series test. All right, so as I do with the alternating series test, I start with the second part and take a look at just the limit as n goes to infinity. Well, the natural log of n plus 1 as n gets bigger goes off to infinity, so 1 divided by larger numbers is heading to 0, which is what we want. And the terms, the natural log function's increasing. Looks, that's a poor approximation, but just to give you a sense of what's going on, looks like this. So if I plug in, how do I want to say this? If I'm plugging in n plus 1 to the natural log function, and I plug in the next number after n plus 1, which is n plus 2, since the natural log function is increasing, then the natural log of n plus 2 is going to be bigger than the natural log of n plus 1. And then 1 over the natural log of n plus 2 is going to be less than or equal to 1 over the natural log of n plus 1. And you might be thinking, so what? I'm trying to get my computer screen to move, and there it jumps on me because it's acting a little silly. Well, this term over here is a sub n, not 0. That's the computer messing with me a little bit. There we go. That's just a sub n. This over here, remember, this is n plus 1 plus 1 in parentheses. So that means this is just a sub n plus 1. And that's what we wanted to show, that the terms are decreasing. So by the alternating series test, this series converges. But unfortunately, it doesn't tell us if it's absolutely convergent or not. We still have some work to do. I have to look at a series formed by its magnitudes. And so if I can get my computer to scroll a little bit. All right, so if I look at the magnitudes, then I get the sum from n equals 1 to infinity. That's just 1 over the natural log of n plus 1. I could start using some of my, tests from the previous section here. You could probably start looking to form some sort of basic comparison test relationship. But I'm going to go right into, because I kind of know how this is going to work out, I'm going to compare this to the harmonic series. So if I look at the harmonic series, you remember from the limit comparison test, I put the series I know something about, its terms in the denominator. So I'll take the harmonic series, put the terms in the denominator because I know it diverges, and I need to get a certain thing to happen. So the limit as n approaches infinity. When I do the division here, I get this. And this is, goes to infinity over infinity. If you want to apply L'Hopital's rule, you can, or you can remember that linear functions, all polynomials grow faster than logs. And so this is actually going to go off to infinity. And so by the limit comparison test, since 1 over n, excuse me, I hope that didn't come out in the audio. Since 1 over n diverges, and this limit went to infinity, 1 over natural log of n plus 1, this series here diverges. And so the original series, sum from equals 1 to infinity of negative 1 to the n over natural log of n plus 1, is conditionally convergent. All right, shall we move on to part C? Again, not begging you, but I'm somewhat telling you need to go try these on your own. So if you haven't done this yet on your own, you're doing yourself a huge disservice. All right, so this is that in part C. It's an alternating series, so I can use the alternating series test. So let's take a look at the limit as n approaches infinity of n factorial over 2 to the m. Something we've talked about before, this goes off to infinity, which is clearly not 0. So this series diverges by the nth term test. No, by the alternating series test, because, sorry, I'm frustrated with technology, but so I'm not paying close enough attention. The alternating series test. I don't know why that shifted like that. My frustration is starting to kick in a little bit. All right, I'm not going to try to fix it because I don't know what's going on. So I'm just gonna finish this recording. I got one more example, and then I'm gonna do a separate video for the last test. This is the last series that we have to consider. Again, it's an alternating series, and so the limit as n approaches infinity of 1 over root n goes to 0, which is what's required in our alternating series test. And again, thinking about the square root function looks something like this. When the inputs are increased, the output is also increased. So root n plus 1 is going to be greater than or equal to the square root of n. So 1 over the square root of n plus 1 is going to be less than or equal to 1 over the square root of n. So a sub n plus 1 is going to be less than or equal to a sub n. So this series is convergent by the alternating series test. So is it conditionally convergent or absolutely convergent? So let's take a look at the series formed by the magnitudes. Hopefully you recognize what this is going to be. This is just 1 over root n. This is a divergent p-series because p, which is equal to 1/2, is less than 1. Less than or equal to 1. That's completely correct. And so the series formed by the absolute value of the terms does not converge. And so the original series, negative 1 to the n over root n, is conditionally convergent. All right. After this, there'll only be one more part. It shouldn't be, only one more part.